Hello everyone. Today we're going to start our set theory mini unit. Today we're going to talk about how we can use Venn diagrams to organize data. Okay, different numbers we can put in different sets based on their characteristics. So we need to start with a few vocabulary terms. Okay, first off, what is a set? What is an element? So a set is a collection of items. Could be letters, could be numbers, just grouped up. So for example, we have the set of even numbers. So every even number would belong to that set. Or in chapter 1, we did the set of integers. So those were all the positive and negative whole numbers. All of them would be entries in that set. And an element is a single entry. So 2 would be an element in the set of even numbers. 4, 6, each one would be an element. Okay, we could also have sets of data. So for example, we could have sets as in a type of clothing. Okay, and an element would be pants, or an element would be socks. We have sets, which are collections of elements. Now we have to deal with the universal set, which is the set which contains all of the objects. So, for example, let's say our universal set is real numbers. That means everything that's a real number is in the whole set. And then we could have subsets, which are smaller categories. So, for example here, whole numbers are a subset of integers because all of the whole numbers are in the integers. The integers is just a bigger set, and we can break it down even smaller. Now we have unions and intersections and complements, which we'll talk about in a few moments. Now, if we're looking at two sets, here are some of the cases that we could have. Now we're looking at this big rectangle is the universe, it's the universal set, and everything else is inside it. We always have a universal set, and then we have subsets of the universal set. So our first example is disjoint sets. This is when set A and set B don't have anything in common. So this example, set A might be even numbers, and set B could be odd numbers. No intersection, no elements belonging to both. Now the opposite of that is equal sets, when set A and B are the same exact set. For example, we could have even numbers for set A and numbers divisible by 2 for set B. Now those are the same exact thing. All even numbers are divisible by 2, and all numbers that are divisible by 2 are even. So they'd be the exact same set. This doesn't happen terribly often. Now subsets, which we talked about in the first chapter of the year, is when we have a set and then there is a smaller set where all of the elements are completely inside the bigger set. So like on the last slide, I said we could have integers, which are positive and negative whole numbers. And in the middle, we just have whole numbers. So here inside, we'd have all the positives and 0, which also belong to B, but B would include some negatives that A does not have. And then we have the most frequent occurrence where they share some items in common. For example, we can look at even numbers and numbers that are divisible by 5. If I put some even numbers here, 2, 4, 6, 8, not divisible by 5, but 10 is, so 10 would go in the middle. So intersecting sets, which is very common, they share some elements, but not all of them. So how we organize our list, I like to start from the center. Let's say our universal set is the integers 1 through 8. So in this universe, the numbers 1 through 8 have to be placed. Now, set A is this whole circle, including the intersection. And set B is this whole circle, including the intersection. So what I look for first is out of these 8, which ones belong to the intersection? Which numbers belong to both A and B? So I see 1, 2, and 4 belong to A and B, so they got to go in the middle. Now, some people like to cross them off once they're used, so they make sure they don't write them twice, because each number can only go in one of the spots. I then see what A has that B does not, and what B has that A does not. So right now I've dealt with 1, 2, 3, 4, and 5, and I'm left with 6, 7, and 8, which are still part of the universe, but they're not part of A, and they're not part of B. So we need to put them outside the circles, but still in our universe. So now this is a representation of where all of these numbers would go in this universal set. Now, there's a difference between the union and the intersection. So the union symbol has got the U. It means it's got to go in at least one of the sets. So if it's in A, it's in the union. If it's in B, it's in the union. And if it's in the middle, it's in the union. We like to use the word or to help describe this. Now, I know in English, or means one or the other, but in math, or, the union means it could be in one or the other or both. So or means at least one. So it's got to be in at least one of the sets. Now the intersection is this upside down U symbol. It's only the intersection, it's only where both sets overlap. So A intersect B is right in the middle. So 3 and 4 are the only numbers in this case that are in the intersection, whereas they're all in the union as long as they're in at least one of the circles. So let's take a look at this example now. This is the same example before. We already have our Venn diagram created, and we need to write which elements belong to the intersection or the union with a complement, and we'll talk about what the complement symbol means as well. So first, I look at the intersection. A intersect B. It's got to be in both A and B circles. It's got to be shared. So that's this region. So the numbers that are in the intersection are 1, 2, and 4. Now we use the curvy braces to represent a set. Now this symbol, which we haven't talked about yet, is the complement symbol. So this means what is not in A. So anything that's not in A, not in this circle, would be part of the complement. So 5 is not in A, and 6 is not in A, and 7 is not in A, and 8. Now the way to think about this is we look at our circle for A, and anything on the outside of the circle, I don't care if it's in another circle, as long as it's on the outside, it's not in A, it's in A complement. Now we've talked about the union. The union has to be in one of the two circles. So 1, 2, 3, 4, and 5. I don't care if it's in one circle or two circles. I don't care if it's in A or B, as long as it fits one of these two categories, it counts in our set. And then A or not B is very interesting because it could be in this A circle, or it could also be outside of B. So as long as it's in the A circle or it's not in the B circle, as long as it fits one of those, we count it. So 1, 2, 3, 4 are in A, and then 6, 7, 8 are in not B. So as long as it fits one of the rules, we count it. So our set for A union B complement is 1, 2, 3, 4, 6, 7, and 8. 5 is the only one that breaks both rules. 5 is not in A, and 5 is in B, so it doesn't adhere to either of these rules. Now, here's a few examples for you to try. We'll see in Schoology, we'll have some exit tickets for you to practice. If you'd like, please email me your work and I will check with my answer key. So we can have two sets, so set A and set B. Maybe we can have 3 sets, where it can have to be in all 3 of them, in the intersection. And here's some for you to try where you have to create the Venn diagram first. So this is the introduction to how to organize sets using Venn diagrams.